It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Emeritus Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on mechanics of unsaturated soils, which will be delivered by Professor Emeritus Delwyn G. Fredlund and Dr. Murray Fredlund. Professor Delwyn G. Fredlund has spent over 50 years conducting research into the behavior of unsaturated soils. Most of his career was spent at the University of Saskatchewan, Saskatoon, where he organized the Unsaturated Soils group for the study of all areas of unsaturated soil behavior. Del Fredlund obtained his BSc degree from the University of Saskatchewan, Saskatoon in 1962. In 1966, Del Fredlund joined the Department of Civil Engineering at the University of Saskatchewan, Canada. In 1973 he obtained his PhD from the University of Alberta. Dr. Fredlund's research studies have resulted in the authorship of two books, namely, Soil Mechanics for Unsaturated Soils, and Unsaturated Soil Mechanics in Engineering Practice, published by John Wiley & Sons. Dr. Fredlund published approximately 500 journal and conference research papers and has delivered many keynote lectures at conferences. He has been the recipient of numerous awards, amongst them the Leggett Award, 1999, the Tursigi Lecture Award, 2005, and the Quigley Award, 2009. He is also a recipient of the Order of Canada and is a member of the Canadian Academy of Engineering.
Anyways, thank you, Dr. Das, for your kind introduction. I count it a great honor to have been asked to deliver the lecture titled An Applied Science for Unsaturated Soil Mechanics. I have spent most of my professional career attempting to assemble a science-based methodology that would allow geotechnical engineers to put unsaturated soil mechanics into routine engineering practice. I have spent over 50 years. It's a long time, and my wife says I must be a very slow learner. But now my challenge today is, in the next 45 minutes, is to explain what I have learned over half a century. Let me give you a brief outline of my talk. I will start my lecture by showing the relationship between unsaturated soil conditions in the field and the simulation tests that we needed to perform in the laboratory. I will describe three pillars that have formed the essential components of a science-based methodology for saturated soil mechanics. And then I will explain the importance of these same three pillars for unsaturated soil mechanics. There are two basic but very important laboratory tests that need to be performed to characterize an unsaturated soil. These two tests are the measurement of the soil water characteristic curve and the shrinkage curve. I'll explain the steps involved in the analysis and the interpretation of the laboratory results. I would note that the step from theory to implementation into engineering practice is indeed a large step. There is one water phase equilibrium condition that assists engineers in establishing a reference linkage between field conditions and laboratory conditions. It is the situation where the net moisture flux at the ground surface is zero. Under this condition, the pore water pressure line is linear from the groundwater table to ground surface. This is true for all soils and is referred to as the hydrostatic stress state. While the equilibrium pore water pressure line is linear, the quantification of the amount of water in the soil will be nonlinear and will reveal two distinct breaks. These breaks occur at the air entry value and at residual suction. These two breaks subdivide the unsaturated soil zone into three subzones. A plot of the amount of water in the soil versus the negative pore water pressure forms the basis for the soil water characteristic curve, or the SWCC. The soil water characteristic curve will later be shown to actually be a family of curves that are hysteretic, that are non-unique. However, first, let us limit our discussions to the drying or desorption soil water characteristic curve. In reality, though, we do not live in a world where the net moisture flux at the ground surface is zero, as I previously assumed. Rather, moisture is either falling on the ground surface as precipitation or leaving the ground surface as evaporation or evapotranspiration. This means that the ground surface constitutes a moisture flux boundary condition. There are several components to the ground surface moisture flux, and each component must be quantified independently when calculating the net moisture flux. Moisture flux at the ground surface disturbs or perturbs the pore water pressure line in the soil. Handling the moisture flux boundary condition at the ground surface adds a new challenge for geotechnical engineers, but it also opens the way for the study of a broad range of new problems that are of interest to geotechnical engineering. The primary objective of this lecture is to propose geotechnical engineering protocols for the determination of unsaturated soil property functions, or referred to as USPFs. The unsaturated soil property functions are constitutive relations that allow geotechnical engineers to simultaneously model the saturated and unsaturated soil zones of a continuum. The implementation of the proposed protocols must meet certain conditions. They must not be too costly. They must be sufficiently accurate in order to add value to the project under consideration, and they must be anchored seamlessly to saturated soil properties. The proposed protocols are estimation procedures. The proposed protocols are estimation procedures that are made possible through the measurement of two unsaturated soils relationships, namely the soil water characteristic curve and the shrinkage curve. The proposed estimation procedures require the adoption of a new paradigm or a new way of thinking on the part of geotechnical engineers. However, this new paradigm appears to be rapidly gaining acceptance in geotechnical engineering practice, and also, as we notice, the increase in research papers at engineering conferences that are related to soil water characteristic curve. Our desire as geotechnical engineers is to develop a science-based methodology for unsaturated soil mechanics. There are three primary so-called pillars that have been used with success in saturated soil mechanics, and they need to be available for unsaturated soil mechanics. First, there needs to be engineering protocols. Protocols are procedures of practice that are based on sound theory and research studies that have been reported at conferences and journals from all around the world. Secondly, there needs to be laboratory soil testing procedures that are not too costly to perform, but which provide the basic information needed for the estimation of unsaturated soil behavior. Third, numerical modeling techniques need to be available since the soil properties are nonlinear and become part of solving nonlinear partial differential equations for which we need computer solvers. Now, during the course of my talk, I would like to give you three opportunities to interact. On the screen is the first poll question. Poll question number 1. Select either number 1, 2, or 3, whichever applies. I'd like to know how many unsaturated soils projects you have been involved with over the past 5 years. less than 5 projects, 5 to 15 projects, or more than 15 projects? Take a few seconds to answer the question. We'll move on. We have a lot of researchers in soil physics who have made significant contributions to the understanding of unsaturated soils. I want to give them honor because their efforts should not be trivialized. The primary soil physics contributions are related to proposed estimation procedures for unsaturated soil property functions. One of the primary soil physics researchers was the man by the name of Clute. In 1965 and 1986, he published a summary describing the complexity of the soil water characteristic curve, but how it could be used to advantage. The soil water characteristic curve was plotted as the amount of water in the soil versus soil suction. He suggested that the soil water characteristic curve actually was consisted as part of a family of curves. And he described them as follows. First, the initial drying curve starts with the soil being forced or wetted to 100% degree of saturation. It's called the initial drying curve. The second curve he mentioned is called the main drying curve. It starts from a naturally wetted soil condition. And the third one is the main wetting curve, defined after the soil has been dried and is then once again wetted. In addition, there were scanning, drying, and wetting curves. And they were contained within the limits of the main drying and main wetting curves. The soil water characteristic curve was recognized to be complex in nature by our friends in soil physics. But still, it was realized to be of significant value in solving unsaturated soil processes. Clute in 1986 described a number of features of the soil water characteristic curve that are proven to be of value in analyzing the behavior of unsaturated soils in general. I want to highlight some of his conclusions that are of value to us. First, he stated, the soil water characteristic curve is a fundamental part of the characterization of the hydraulic properties of a soil, thus forming the basis for estimation procedures. Second, soil suction was explained to be an energy per unit volume, and as such can be referred to as a pressure. Third, soil suction could be defined as matrix suction up to around 1,500 kilopascals, and then as total suction in the range from 1,500 kilopascals to 1,000,000 kilopascals. Fourthly, the amount of water, he said, could be expressed in terms of a weight or mass basis, a volume basis, or degree of saturation basis. Fifthly, the soil water characteristic curve was described as a family of curves that exhibited hysteresis, but it was suggested that unsaturated soil behavior should first be understood in terms of the main drying and wetting curves. This is a brief summary of Professor Clute's key findings that have been of relevance for geotechnical engineering, but I think it is important that we evaluate all these findings of our friends in soil physics and see whether or not they need to be modified or are they acceptable for us in geotechnical engineering applications. The proposed procedure for calculating unsaturated soil property functions begins with performing two basic laboratory tests. It first involves measuring the drying branch of the soil water characteristic curve over its entire range as shown on the left-hand side of this slide. And secondly, measuring the shrinkage curve, shown on the right-hand side of this slide. The results of these two tests need to be blended together because the initial measured volume and mass conditions might be slightly different. Once the initial results are blended, all other volume mass versus soil suction relations can be computed. The entire analysis involves performing these two tests and calculating fitting parameters for unsaturated soil constitutive equations. Necessary calculations can readily be performed using an Excel spreadsheet, or they can be solved using the commercial software called SV Soils. Actually, there are 3 tests required to obtain the basic soils information required for calculating the unsaturated soil property functions. A pressure plate apparatus is needed to measure the gravimetric water content versus matrix suction in the range from a few kPa or few kilopascals up to 500 or 1500 kilopascals. Then the measurement of the total suction versus water content relationship is required for the high suction range. And it requires the use of a vapor equalization technique. Another test involves the measurement of the shrinkage curve. So these 3 tests really provide a means of calculating all other volume mass soil water characteristic curves for the drying mode. The commercial cost to measure the combined drying soil water characteristic curve and the shrinkage curve on any soil is generally in the order of $1,200 to $1,500 US. The right-hand side of this slide shows several pressure plate apparatuses that were developed at the University of Saskatchewan and then used commercially. This commercial lab had about 30 apparatuses like this that were running a lot of the time. The pressure plate cells make use of the axis translation technique and can apply suctions up to 500 kilopascals. The soil specimens tested are similar in size to those used for one-dimensional consolidation testing. 1 to 3 days are generally required for suction equalization under each applied suction. A manufacturing company, GCTS, in Tempe, Arizona, has developed a pressure plate apparatus that extends a range of applied suctions to 1,500 kilopascals. The GCTS apparatus also has a number of special features. First, a vertical total stress can be applied to the soil specimen under K-naught loading conditions. The applied total stress makes it possible to more accurately simulate in situ field conditions by applying total stress. But more importantly, vertical displacements can be measured and the overall volume can be calculated. The water volume can be calculated at any suction, and the diffused air volume can also be independently measured throughout the test. There's also been some other apparatuses that are somewhat similar that have been built in other countries of the world. So this is not the only one available. This slide shows soil water characteristic curves measured on 3 supposedly identical specimens of a low compressibility silt. Several points can be gleaned from examining the results. First of all, the results of all 3 tests can be shown to be very reproducible. Secondly, the air entry value from the drying curve is clearly identified to be about 10 kPa. And the residual suction can be seen to be about 120 kilopascals. Third, the hysteresis drying curve and the wetting curve appear to be congruent or parallel on a semi-log plot. And they are, in this case, about 1/3 of a log cycle apart. I would also note that each of the three soil water characteristic curve tests, drying and wetting, required about 2 months to perform. In other words, pressure plate tests are time consuming, and measuring both the drying and wetting soil water characteristic curves may not be acceptable for many geotechnical engineering projects. However, I would note that the primary information required by the geotechnical engineer can be obtained from the drying branch of the soil water characteristic curve. And by information, I'm referring to the air entry value, the rate of desaturation, and residual conditions. The relationship between water content and total suction in the high suction range can be obtained using vapor pressure equalization on small soil specimens. The chilled mirror potentiometer from Decagon, the company is now Meter, has proven to be very valuable for obtaining the necessary data in the high suction range. The procedure involves preparing a series of small soil specimens at slightly different water contents. Some specimens are prepared by adding small amounts but varying amounts of water, while other specimens may be allowed to dry for varying elapsed times. Once moisture equalization has been achieved, each measurement of total suction requires only a matter of minutes. Suction measurements can be made in the range from a few hundred kilopascals to more than 100,000 kilopascals. Let us now consider the steps that need to be followed for the interpretation of the main drying soil water characteristic curve data. Let us keep in mind that our final objective is to use this information for the estimation of unsaturated soil property functions. Also note on this graph that there is an arbitrary vertical line at 1500 kilopascals. Below this line, matrix suction data are plotted versus gravimetric water content. Total suction data are plotted versus gravimetric water content for suctions greater than 1500 kilopascals. The two water content versus suction data sets constitutes a basic thumbprint for the drying behavior of the soil. At first, it may seem rather unusual to plot both matrix suction data and total suction data on the same horizontal axis, but experience has shown that it works quite well. Now, we need to find a continuous mathematical function that can be used to best fit the data set over the entire suction range from 0.1 kPa to 1 million kilopascals. Most soils show a typical S-shaped sigmoidal behavior on a semi-log plot. I would also note that data on some soils shows a bimodal shape. The 1994 Fredlund sigmoidal equation, along with a correction variable for high suctions, has been effectively used to best fit both unimodal and bimodal data sets. There are three fitting variables from the Fredlund and Zing equation that can be quantified using a regression analysis. One variable indicates the inflection point, which in this particular case is, you can see, is 74.24 kilopascals. Another variable indicates the rate of desaturation, which in this case has a value of 1.573. And there is a third variable that proves the general fit in the high suction range. The residual suction can be approximated to be about 1,000 kilopascals. I would note that other empirical equations could also be used to best fit the data, provided they fit adequately over the entire suction range. An Excel spreadsheet can readily be programmed to perform best fit regression analysis on the experimental soil water characteristic curve data. This is done through the use of the data pull-down menu, which is part of the Excel software. The red circle in this slide identifies 3 fitting parameters that have been quantified through use of the regression analysis. The correction factor, capital C, forces the Fredlund equation through a fixed point of 1 million kilopascals at 0 water content for all soils. Once the regression analysis is complete, the gravimetric water content versus soil suction data can take on a new form, the form of a single valued continuous mathematical function for all possible suctions. Many geotechnical engineers may not be familiar with sigmoidal types of equations. However, I would point out that most equations that have been proposed for soil water characteristic curve data are actually similar in form. Now I'd like you to ask poll question number 2. How many soil water characteristic curves, or SWCCs, have you or your laboratory measured over the past 5 years? Less than 5 tests, 5 to 15 tests, or more than 15 tests? You can register your response. Once the gravimetric water content versus soil suction data has been collected and analyzed, there's one important question that the geotechnical engineer must respond to. The question is as follows: does volume change occur in the soil as soil suction increases? If the answer is yes, then it is important to also measure the shrinkage curve. On the other hand, if the answer is no, then the shrinkage curve is not required when analyzing the drying curve data. Historically, in soil physics, it has been common practice to always assume that there is no volume change in the soil as soil suction increases. This assumption is not adequate for most geotechnical engineering applications because water content changes produce changes in 2 things. They produce changes in overall volume or void ratio or changes in degree of saturation. Volume changes and degree of saturation changes constitute 2 different physical processes in the soil and must be independently taken into consideration for geotechnical engineering applications. Soil specimens for the shrinkage curve are commonly about 3 centimeters in diameter and about 1 centimeter in height. The soil water characteristic curve specimen and the shrinkage curve specimen are initially allowed to imbibe water until their matrix suction reaches a 0 value. The shrinkage curve test specimens can be formed into a metal ring with an open top and bottom. The specimen is then allowed to lose moisture through evaporation to the atmosphere. The diameter and the height of the shrinkage curve specimen can be measured at various elapsed times of exposure to evaporation. Usually about 2 sets of measurements can be made each day, and after a few days, the specimen can be oven dried. Shrinkage curve data can be plotted as void ratio versus gravimetric water content. As drying commences, the shrinkage curve starts following a near constant degree of saturation line, and then it bends horizontal and takes on no slope as it comes to 0 water content. When it's completely dry, of course, its suction is 1 million kilopascals. The shrinkage curve data can now be best fit using a hyperbolic type function of the type proposed by Murray Fredlund in 2000. There are 2 independent fitting parameters for the hyperbolic function. The ASH variable corresponds to the minimum void ratio attainable upon complete drying, and the SH variable defines the sharpness of the curvature as the soil goes towards a completely dry state. The third variable is calculated from the plasticity of the soil. An Excel spreadsheet can, once again, readily be programmed to perform the best fit regression analysis on the experimental shrinkage curve data. The red circle on the slide identifies the fitting parameters which have been quantified using the regression analysis. The shrinkage curve data, for the shrinkage curve data. Once the regression analysis is complete, the void ratio and gravimetric water content data take on the form of a single valued continuous mathematical function. It should be noted that in some cases it is sufficient to estimate the shrinkage curve based on the plasticity and the shrinkage limit of the soil. With the soil water characteristic curve and the shrinkage curve represented as mathematical functions, it is now possible to move towards calculating other volume mass versus suction functions. For example, it is possible to calculate the void ratio versus suction relationship, the volumetric water content versus suction relationship, degree of saturation versus suction, and other functions such as dry and total density versus suction. However, the primary objective of the analysis is to define unsaturated soil property functions, such as the permeability function, the water storage function, the shear strength function, volume change functions, as well as other material property functions. Taking hysteresis into consideration involves repeating the above-mentioned calculations, this time using estimated or measured wetting branch data for the soil. It is beyond the scope of this lecture to do more than briefly describe how hysteresis might be accommodated. I will say a few words later. The first unsaturated soil property function to be calculated and plotted is the void ratio versus soil suction. This function is obtained by substituting the shrinkage curve equation into the gravimetric water content versus suction equation. The plotted results on this slide show volume change starts to occur in the soil when the suction reaches a value of about 20 kilopascals. And most of the volume change ceases when the soil reaches about 300 kilopascals. The total volume change upon drying can be calculated to be about 20%. The volumetric water content versus soil suction function can be obtained by combining the gravimetric water content soil water characteristic curve and the shrinkage curve as shown by the equation on the slide. The volumetric water content versus suction provides a convenient form for defining water storage of the soil in the soil. The volumetric water content embraces both overall volume change and changes in degree of saturation as suction is increased. Water storage is defined as the slope of the volumetric water content function. Therefore, the water storage function can be obtained by differentiating the volumetric water content versus suction relationship. The water storage function can be seen to be highly nonlinear with relatively low values in the low and high suction ranges. The maximum change in water storage occurs near the inflection point of the volumetric water content function. Probably the most important volume mass relationship is the degree of saturation function. The degree of saturation function is equal to the gravimetric water content function divided by the shrinkage curve equation, while marching forward with the increases in suction to a maximum value of 1 million kilopascals. The degree of saturation function can be seen to differ somewhat from the gravimetric water content function. The true air entry value of the soil should always be defined using the degree of saturation function, not the gravimetric water content function. The degree of saturation function generally shows a more distinct break, as well as yielding a higher air entry value than what you would get if you analyze the gravimetric water content relationship. Physical properties such as the coefficient of permeability are known to change very significantly and very rapidly with changes in degree of saturation. The calculated degree of saturation versus suction relationship, once it's calculated as a series of data points, can once again be refit with the Fredlund and Zing equation, yielding a continuous function for the degree of saturation. In fact, all volume mass versus suction functions can be best fit using the same Fredlund-Zing 1994 equation. The degree of saturation function can be replotted using a log to the base 10 scale on the abscissa. In this way, the suction is converted to a linear scale, making it easier to calculate the true air entry value of the soil. The air entry value is defined by drawing a line tangent through the inflection point, and where it intersects the horizontal line through the low suction range data defines the true air entry value. In this case, the air entry value is 147 kilopascals, a much larger value than observed on the gravimetric water content function. It is also possible to derive a closed form equation that will allow you to calculate the air entry value as shown on this slide. It is important to pause at this point to ask the question, why do I need various volume mass versus suction relationships for the soil? I would like us to examine the partial differential equation that can be used to solve transient flow through saturated or unsaturated soil systems. The equation at the bottom of the slide contains two soil property functions. They're encircled in red. The one is the permeability function, K. M2W is the water storage function. The primary difference between saturated and unsaturated soil water seepage analysis lies in the fact that the properties have the form for an unsaturated soil of being nonlinear functions. This has the effect of making the solution of the partial differential equation iterative in nature. In other words, values for the soil properties must be first assumed while solving for the hydraulic heads, H, at all nodes in the finite element grid. Then the soil properties must be upgraded, and once again, the partial differential equation has to be solved for new hydraulic heads and pore water pressures. And the process is continued until convergence is achieved. On this slide, you can see that permeability can be a function of degree of saturation and void ratio. Water storage is a function of volumetric water content. So you see why we need those two laboratory tests. Finally, I'd like to ask you a third poll question. What types of projects have you encountered in unsaturated soil mechanics? Have you been involved in water balance or soil cover designs, swelling and expansive soils problems, slope stability problems, and I should just say other problems? Pick the one that is the most common problem you have encountered. Take a few seconds to do that. So let's take a look at the permeability function. The permeability function can be obtained by integration along the degree of saturation function using the procedure proposed by Fredlund et al. In 1994. The permeability function is seen to remain as a constant value up to the air entry value of the soil, which was 147 kilopascals. The permeability function can be calculated as a relative permeability function, starting with an arbitrary value or a value of 1.0. The function can then be scaled downwards in order to make it start at the actual saturated coefficient of permeability value, as shown on the slide. Next slide, it'll show that. This slide shows the relationship between the relative permeability function and the actual permeability function. The actual saturated coefficient of permeability for the soil was assumed to be 1.0 times 10 to the minus 2 meters per second. This actual permeability function applies for the drying process of the soil. This graph also shows the importance of accurately identifying the true air entry value of the soil. The soil behaves essentially as a saturated soil as long as the air entry value is not exceeded in the soil. Excuse me. Let me now give consideration to the hysteresis effect associated with wetting and drying processes. First, it should be noted that the effect of hysteresis on the permeability function can be estimated based on the hysteresis loop associated with degree of saturation versus suction. Let us suppose that the magnitude of the hysteresis loop can be quantified by the shift in the inflection point. And let us assume that the drying and wetting branches of the degree of saturation soil water characteristic curves are congruent. The epsilon value in the equation at the bottom is simply the equation you can use that allows you to indicate how much of a hysteresis loop and quantify it as a percentage of a log cycle. The shift in the wetting curve in this slide is assumed to be 35% of one log cycle. So if that is the wetting curve, now let us recalculate the permeability, wetting curve permeability function, and it'll be shown on the next slide. The drying and wetting branches for the corresponding permeability functions are shown here. The estimated permeability functions are based on several assumptions and are by no means a rigorous formulation. However, they provide a starting point that is acceptable when considering the effect of drying and wetting on the coefficient of permeability. My lecture is mainly focused on the application of soil water characteristic curves to seepage problems. However, before I close, I would like to illustrate the application of the soil water characteristic curve for the estimation of shear strength of an unsaturated soil. It has long been observed that the shear strength of an unsaturated soil is related to the degree of saturation. Research studies have showed that the soil behaves as a saturated soil up to the true air entry value. At this point, the shear strength envelope becomes tangent to the saturated shear strength envelope, and then it starts to bend over. It has also been observed that the slope of the shear strength envelope approaches zero near residual suction conditions. These 2 points are really anchor points, and they are estimated from the soil water characteristic curve. We use the soil water characteristic curve, the degree of saturation branch, to give us the anchor points on the shear strength envelope. As I conclude my lecture, I realize that I've had you sign on to many assumptions as well as some new theory. However, I strongly believe that the path forward, by path forward I mean the implementation of unsaturated soil mechanics in geotechnical engineering practice, must involve the use of smart approximations and assumptions. based on research studies that have been undertaken and published at conferences and in journals around the world. I am convinced that the dry soil water characteristic curve and shrinkage curve provide sufficient information for the determination of all volume mass soil property functions. And I'm also convinced that unsaturated soil property functions such as permeability, shear strength, and volume change can be estimated with sufficient accuracy for most geotechnical engineering applications. I would be willing to answer any questions you may have. Okay, what is the difference between pressure plate test in the low suction range and triaxial test? There is no difference because in the triaxial test, you're going to still install the air entry value, high air entry value disc in the base plate of the triaxial cell. And in either case, when you're using a pressure plate or triaxial, the volume change associated with changing suction is going to be three-dimensional. And so whether you put it in a pressure plate or a triaxial cell, you should get the same, essentially the same water content versus suction relationship. Next question. For a given soil, if we measure the gravimetric water content from several samples at different initial void ratios, they will lead to the same curve? For example, of testing in all the main drying curve. Well, I think I know what you're talking about. Yes. If you get to, of course, as you go to a completely dry condition, all of those soils should dry to zero water content at 1,000,000 kilopascals. At lower suctions, before you get to 1,000,000, the curves will tend to converge. It is a little bit like taking a soil and saying the soil has a pre-consolidation pressure. But this, it's not the pre-consolidation pressure now, it's the air entry value that tells you when the curve will bend downwards. So they might start at initial different void ratios, and as they go by the air entry values, which will be not necessarily that different, and then they will tend to converge onto the same curve. I think that's what you were asking, and that's my answer. Okay, could you please share your views on integrating shrinkage data of the specimen while establishing its soil water characteristic curve? There is an effect from size, boundary conditions, pore fluid chemistry on the shrinkage behavior of soil. Should we ideally be using the shrinkage data from a specimen that is of equal size and density under similar boundary conditions? Okay, between I think you're referring to the difference in the size of the sample you use for measuring the soil water characteristic curve. It's about the size of a consolidation sample. The shrinkage curve is much smaller. Is there a difference? Is it a problem? Size difference? And the answer is no, not really. You see, the size of the shrinkage specimen was really dictated by the original shrinkage limit test. And the reason they took a small sample was in order to have an intact portion of the sample without a crack, because if a crack forms in the specimen, you can't measure the volume very well. So it was purposely made smaller so you could have an intact portion. And it's the most important value on the whole shrinkage curve is what's going to be the minimum void ratio of an intact piece of soil. And you can have the shrinkage curve done on a small specimen and the soil water characteristic curve on a large, and I don't think there's any inconsistency. But it'd be worthy of further research, but that's the reason why we use a small sample to get around the cracking problem. Shrinkage behavior of the soil is hysteretic. So when we establish secondary drying wetting curves, should we rather use the shrinkage data from the respective cycle of drying and wetting? Let me put it this way. There is some hysteresis on the shrinkage curve testing, but it is not as significant usually, but we really don't know how to include the hysteresis on the shrinkage curve data. There was limited results. There was a PhD study done on that by Tripathy, a very good work. And, but there needs to be more research on the hysteresis on the shrinkage curve part. I think that's all I'll say about that. Let's go. Although there are different processes, is there any attempt to correlate consolidation behavior with changes in void ratio during drying? So I assume by consolidation you mean loading in an odometer or a triaxial cell, and to get those void ratio changes, comparing with drying. Okay, if we go right back to some of my work in the late 70s, I showed three-dimensional plots where you put total stress on one axis and suction on another axis and produce these three-dimensional diagrams. Yes, consolidation behavior is different. Consolidation has its own characteristics. Consolidation curve may have a pre-consolidation pressure, it may be reloading. All those are characteristics of it. As far as the drying is concerned, it may not even care about the pre-consolidation pressure. The air entry value is an independent variable. So there are differences, yes. Next. The physical meaning of air entry value. The meaning that is, let me say, most meaningful to us as geotechnical engineers is the value where air starts to enter the biggest pore on the soil. It's very difficult to identify exactly what that suction would be. And so we use an empirical construction in order to define the air entry value. It makes most sense to define it on the drying curve from the degree of saturation drying curve, because that is the point at which air enters. Now, I showed more than one. I showed an initial drying curve and a main drying curve. You could do the air entry value on either of those two, and usually they're just about the same value. Importance of unsaturated soil and considered in seismic geotechnical design. There are questions related to unsaturated soils and seismicity that, as far as I know, I really have not been fully addressed yet. Even questions asking about what's the difference in seismic behavior if the soil has some error, if its degree of saturation is low, how does it affect liquefaction? How does it respond to seismic? I think the research is still to be done on that. I have nothing to really add about it. I just know it's an area needing research. I'd like to know if the parameters obtained from the filter paper tests are as reliable as the tests explained in your presentation. No, the answer is no. But with filter paper, you can try to measure matrix suction values. That is very difficult to get good values because it's hard to get perfect contact with the soil. and a few little soil particles change the mass of the filter paper, so it's hard to get matrix suctions, and total suctions are better, but they're not as consistent and do not have a small amount of scatter in the data, not like the Decagon's little meter that measures total suction very quickly. It's much better. Problems due to saturated soils are more conservative. Why do we work with unsaturated soils again? Well, it depends on what kind of questions you want to answer. I can give you lots of examples, but I'll just give you one. Supposing you lived in Hong Kong on the slopes, and the slopes have suction values, but that suction could disappear due to infiltration during typhoon season. The trigger for instability is a particular suction, when a suction value is reached, when it rains a certain amount over a long enough period of time, the slopes can become unstable. In other words, the trigger for instability is hidden in the unsaturated soils. It would make no sense to do saturated soil mechanics, because then all the slopes in Hong Kong would not even be standing. They are standing because of suction. So that's a whole lecture in itself to explain why saturated soil conditions are not always conservative. They do not allow you to get the kinds of answers you want to get. You wouldn't design roads on completely saturated conditions. You wouldn't. Roads function because there's suction in the soils. Next. In some heap leach projects, I have seen that represent a bimodal pattern. Can you speak something as to why this occurs and how it can be fitted? Well, if there's bimodal soil water characteristic curves, there's going to be bimodal distribution of void spaces. There are some large void spaces and there are some small. And so they give you two peaks in terms of the void distribution, and there'll be two peaks, and there'll be two humps on the soil water characteristic curves.